last video is here, so let us continue. So what I promised is that we should look at a few examples, the simplest examples, how the Fourier series, the classical Fourier series would look like if we deal with some nice functions or interesting functions f. So first, let me comment on what the periodic extension really is, right? So if you have a function defined on the interval, then simply we just copy the same values by shifting the arguments, right? And therefore, from a function defined, for example, on minus tt, where capital T is the period we want to see, we'll simply extend it everywhere. So if we for example take the famous Heaviside function, which is so useful, it's also useful in machine learning and similar things, because it's a function which jumps from some value to some other value. So usually you don't want to see the jump, so you simply have the activation functions by done by some either smooth or continuous approximation, which is continuous, but it's something like a Heaviside function. And so if you look what it does is, it does the following. So we've got, say, the usual setup for x and y, and the Heaviside function, well, here will be minus t half, and here will be plus t half, and the function will be minus 1 here and plus 1 here, right? Well, too much. And if we periodically extend it, then it will be this way and this way and this way. And there are simply the jumps here which we do not have as values. And it actually doesn't matter what we assign as value in these jumping points, because the integrals, when computing the coefficients an and bn, they don't see a change of the value of the function in one point. So who cares? But you see that there are these jumps, so it's essential to have these piecewise continuous functions only. So you also can see other versions of the Heaviside function just jumping from 0 to 1, but we choose here this nice thing, because the result what we get is usually called in the engineering literature the square wave function. So it's something which imitates a signal which is for some time on and for some time off, or goes for some time one direction and for some time the opposite direction, there and back, right? So this is definitely imitating the signal very nicely. And here it's a very simple function, so we can very explicitly compute what the bn's and an's are. So first of all, you see the function is odd, so only the odd coefficients make sense. So the an's will be all 0, no an's at all, right? So that's good. So we see that what we obtain is we get the bn as the integral. Well, so I just took t equals 2 pi right here, so t is 2 pi for the computation. So we go from minus pi to plus pi, and you see, because g is odd and sine is odd, then the product will be even. So in total we shall get twice the integral from 0 to pi from sine nx, and that's very easy to compute. It's this, right? So you see that it will be for even n it will be 0, and for odd n we shall get 2 times 2, which is 4 over pi, and then what's left is the sine x, 1/3 of sine 3x, 1/5 of sine 5x, etc. This is a very straightforward thing, how the Fourier series looks. And from the theorem we know that it will be pointwise converging to G everywhere except the jumping points, and we can say everywhere if we add the value at the jumping points to be the middles, which we know the series will converge to. So we add the value here this way, then we get pointwise convergence to the function everywhere. So this is nice. So let's have a look how it really works. So this is, so here on the left hand side, this is what does it do? It doesn't do what I want, doesn't matter. So what it does is, you see that it imitates the function quite well already if I take 5 terms. So it just wiggles, but roughly speaking it just imitates the behavior relatively nicely. And notice that here it just jumps too high, so it should be jumping from -y to +1, and nearby to 0, what's the jump point, it starts with much lower than -1. It's something like nearly -1.2 and ends at nearly 1.2. So this you would say this is because I have taken only 5 first terms, right? But if I take 50, I get this picture, and you see it gets much nicer here in the middle, but still it jumps exactly as high as here. And this can be computed explicitly, that what's the maximum of all the approximations, and it will always be the same, roughly 1.2 for the Heaviside function, and it's called the Gibbs effect. So the Fourier series at the places of jumps simply makes this mistake of overshooting lower and higher, right? So this is the Gibbs effect. And if I come, well, not today, but maybe later, I will add some comments about the proof. So when we shall be proving the theorem, or if you read through the proof, you actually find the explicit construction how the partial sums are computed. And from that it's clear not only that it happens in this case, but it's clear that a similar phenomenon, roughly speaking the same phenomenon numerically, must appear for all the functions with jumps. And the overshooting is proportional to the jumps. So this is how the Heaviside function would be approximated. And also you see that near to the jumps, the convergence is pretty slow, because the more of the terms I take into the series, so the bigger the partial sum is, the better the approximation will be everywhere except at the jumping points, because there the mistake will become closer and get closer and closer to this. So you will have to be, if you are close, say after some time it will be pushed further to the jumping point, so you will get any precision you want by the approximation, but it will be pretty slow. Whereas, as we told, in case of the continuous functions, the convergence of the Fourier series will be pointwise uniform. So it will uniformly converge, which is a big difference. Right, so of course, if we just move to the general T, not this one, but the general one, then the result which we get is the omega, the phase frequency. So omega equals 2 pi over t is the ratio between the standard frequency and the period and our period, will appear here as a numerical rescaling constant. Right, so that's easy. And just if you want to approximate some given function by Fourier series, then it's very wise to try to choose your period for the periodical extension in such a way that the resulting function will become continuous, right? So for example, imagine the task we are given, say in a small task for an exam or homework, would be just to approximate x squared on the interval 0, 1, right? So we should just have a look what it means. So we have 0, we have 1. Oh no, not that far, so I wouldn't come there. We have 1, and we have the function x squared. So x squared will look like this. This is again 1, right? Not very nice picture, so let me do it again. So it will be like this. So here is 1, right? So, and if I take 0, 1 as the period, then what I would get would be just starting again this way and then again this way, and you see it would be jumping here. Whereas if I decide that I would just rather do it on -1, 1, then what I do by extending periodically will be a continuous function. So definitely, even if someone wants me to approximate on interval 0, 1, I will better go for interval -1, 1 and write the Fourier series for that. And that's what's done here in the example, right? So I compute it now a even function, so there will be just the cosines there. So I will get the AN, so here you have them. And the A0 is to be computed too, so it's this one. So you see that the series will be this one, quite nice. So you just plug in, so P, pi, and X, and yeah, pi is there because we changed the frequency, right? So it's from -1 to 1 instead from -pi to pi. So and by Weierstrass criterion, this series converges uniformly. We see it, and we know that the gx is continuous. Yeah? And by theorem, we already went through, it must be converging to the right thing, to the x squared. So you see that our series really approximates the function x squared on the interval 0, 1, and it's a very nice way how to do it. Well, look what happens if just a comment, look what happens if you put x equals 1 there, right? So then you have cosine pi n, and cosine pi n is known what it is. It's either +1 or -1, so you will get, and you can just throw the things to the other side. So you see it's unfortunate here because of this, but it's pi squared over 4 g in 1 minus 1/3, which we know how much it is. So it's pi squared over 6, right? Because g in 1 is 1, so it will be pi squared over 6 if you compute it. And here inside you will get this thing, and it's always only to 2n, right? So you either get 0 or it gets, well, it always gets this, because it's -1 to n is there, and there will be another one. So you see that by some accident, by just noticing it, we computed how to get the sum of n to -1, -2, which otherwise would be very difficult to guess, right? So you know that this is quite important thing which pops up quite common, right? So that's what we get here. We can go on a little bit. So we have got the x, right? So this is x squared. And now we have got the function x. So how shall we get x? We can get it because we know that the function g, which is x squared, is given by a series which converges uniformly. So we can get x by differentiating. So definitely you see immediately that x must be this one. Of course, we could have computed it just by computing the b's, right? Because it's x, so it's odd, so the a's would be 0. So, but you see, it's useful to know that it can be done that easily. And what about the cube of x? How would be the, it's again an odd thing, how would be the Fourier series of that one? So we can get them by integrating, right? So if we integrate, we get this plus this. So that will be again valid for -1, 1 interval, but it's not valid elsewhere because the function is no more periodic, right? So if you differentiate something periodic, it will remain periodic. If you integrate, it won't. So in order to get the Fourier series for x3 on the interval this way, we have to plug in the approximation to x. But if you do that, you will obviously get that it can't be uniformly convergent anymore, because there will be the jumps, right? So if you look at what the x cube will do on -1, 1, so it will be this guy, and it will go like this and this, right? That's again 1, 1, and so the periodic extension will be just going this way. So there will be the jumps, and it will behave like the Heaviside function, but you can get it by plugging in. Right, so in general, what I was telling about the odd and even behavior of the functions suggests that we would think about the sine and cosine Fourier series. So if you forget either the b's or a's, you get simply the best even or the best odd approximation, and if you know that your function is already of that kind, you can get it. And also what you can do is you can first split your function into the even and odd part, and then do the thing. So I think that's all I wanted to tell for this week, and I will think about coming back to the proof later when we talk about the convolutions and these kind of operators, because they happen to be very important there. So thanks a lot for your attention, and let's see us soon again.